All right, so hello everyone. Welcome to the Kubernetes SIG IBMCloud meeting today on September 26, 2018. My name is Sadeh Jala and I'm one of the SIG leads along with Khalid and Richard. And I'm your meeting host today. Please keep in mind that this is a public meeting and it is being recorded, and this recording will be made available on the YouTube channel. So please be considerate of what you say. I have put the agenda link in the chat. So if anyone has anything to add, please go ahead and do add. Three regular attendees of SIG not going to make it today because of the Kubernetes conference workgroup meeting, which is conflicting with this time. But other than that, if you look in the agenda, we have Animesh Singh volunteered to give a talk on Fiddle and just give an overview and how Fiddle leverages Kubernetes for deep learning workloads. So Animesh, thank you so much for joining today. And it's to you now. Whenever you're ready, we can start.
Yeah, no, thanks Adeh, for having me here to talk about Fabric for Deep Learning, or Fiddle. I mean, it's a project in the AI, machine learning, and deep learning space, but has a strong tie-in to cloud and to Kubernetes in particular, right? So that's the context of the discussion we are going to have. I also have with me Tommy Lee from my team. So essentially, we gave a talk, I would say last month, at the Open Source Summit Vancouver. So that was our talk, which we are going and trying to condense it in around, hopefully 20-25 minutes here. So let me just get started with that. Okay, so the topic of our talk is going to be, how do we deploy and use a multi-framework distributed deep learning platform on top of Kubernetes, right? So it's about Fabric for Deep Learning, or Fiddle. It's available in the open source, github.com/IBM/Fiddle, FFDL, and that's how we pronounce it. Myself and Tommy, we are part of a group called CODE, and CODE stands for Center for Open Source Data and AI Technologies, and it is structured around the concept of code, content, and community. We work across the AI lifecycle and the projects in the open source across that lifecycle around data gathering phase, model creation, model training phase, model deployment phase, and contributing to different communities around that, like Jupyter, Spark, and then also contributing our own IBM open source projects in the community, like Model Asset Exchange, Fabric for Deep Learning, very recently AI Fairness Toolbox, AI 360 Kit, right? So Model Asset Exchange, another counter part project in the CODE umbrella. It essentially gives you a library of deep learning models which are ready for deployment and inference. Very strong focus on the provenance and the history of the models. So make sure that the licenses of the models itself, the licenses of the data sets on which they have been trained on, is being taken into account. Plus, very quickly be able to inference and deploy it using either the containers or Kubernetes service. And now, going forward at WML, Watson Machine Learning. Jupyter Enterprise Gateway, that's again a project which we are heavily involved in, and it's sits at that interface for Kubernetes as well, where essentially you can use local Jupyter notebooks to do interactive creation of deep learning models, do interactive debugging, and be able to launch it across a backend, which is a Kubernetes backend or a Spark backend, and then be able to share resources. So Jupyter Enterprise Gateway is part of our many product offerings within IBM, and this is a project which IBM incubated and is driving in the community. It's now a top level project in Apache, Jupyter ecosystem. Adversarial Robustness Toolbox. This is something which we launched in the first half of the year. It has taken great traction. It's around being able to find vulnerabilities in your model. So it implements state-of-the-art attack methods so as to launch attacks on your models. And then, after it finds vulnerabilities, you can then implement some defense mechanisms, right? So it's, again, available on GitHub, pretty good traction on that. And then definitely, some of the popular open source projects like Apache Spark, where we are heavily involved and contributing, which is, the source of all the IBM products in the analytics and AI space, starting from, Studio, Analytics Engine, Apache Spark service. Spark is embedded through our portfolio. Today, so we are going to focus on Fabric for Deep Learning, or FRIDL. And before I go into, FRIDL, just a brief background around, AI and deep learning in general. So as we can see, and we all are noticing, machine learning and AI is everywhere. We are using it day to day in our lives now. It's no longer, in research papers, in vision. As we are using speech recognition on our mobile phones, we are, driving or not driving autonomous vehicles. We are using facial recognition to unlock our phones, automated fraud detection for protecting our credit, right? It's now impacting our day-to-day lives. It's being used in our day-to-day lives. If you see, the sense of Google Trends, right? Deep learning is something which has revolutionized machine learning, and the trend has risen considerably and exponentially in the last couple of years. More so, if we see 2012 was the inflection point where deep learning starts becoming, very mainstream. That was when, AlexNet was launched, and that was the first real implementation of, deep learning with using GPUs. And even before that, there was a lot of work. For example, IBM Deep Blue, Beat the Champion, Gary Kasparov in chess. Then we had Jeopardy, then Apple Release City, but none of these used deep learning. 2012 was that inflection point, and 2015 was when it became very popular, when Facebook actually launched, widespread facial recognition using deep learning. So that was the inflection point, and then Siri started using deep learning, and now we had AlphaGo last year, and then we had IBM Project Debater this year, which came in as well. And there is a lot of advances happening both on the tooling side, definitely, Coursera, Audacity, a lot of these online training universities are now, creating the next generation of AI developers and data scientists, and the tools are evolving, and that revolution has started to happen now. Now, if we look at, the capacity, what deep learning can achieve today, I mean, it's essentially, we are training artificial neural networks. And if we see, the capacity of deep learning right now, we can train around, 25 million neurons, 100 billion connections. Compare it with a human brain, which has 200 billion neurons, 32 trillion connections. So we are looking at 0.001, 0.003% in terms of the neurons and connection. And in spite of having, so much, or in spite of achieving so much less from a brain capacity, we're still able to do so much with respect to, the current capabilities which are there in deep learning. So that's commendable. So for a lot of us, the question comes, what is an artificial neuron? Typically, think of them as calculators, give them certain inputs, and then, it gives you a certain output. Now, within that, for example, let's take a case, how do we humans recognize numbers, right? We look at patterns, and then, even if there are patterns and variations within those patterns, we are able to tell very clearly this is a number 8, or these are, on the right-hand side, the numbers 4. Now, probably, we decompose it into subparts in our subconscious mind or in our conscious mind. How can we teach this to a computer, right? So when you feed this to an AI system, right, you are essentially feeding its pixel. So if you look at, a 28 by 28 pixel image, then you are essentially giving something like, 784 pixels, or something like that. And then, that's what you have to teach. And did I get stuck on this? Okay, yeah. So in that case, if you look, when a computer looks at this pixel, it looks at the variation, right? So essentially the parts of this particular image, which, are moving between 0 and 254, that's the area where it learns to focus on. And you see the number in the variations, right? Going all the way from 0 and between 254 is where it sees, the activity happening, and that's what it starts recognizing. So now when you need to convert this into a deep learning model, what you do is, you take a neuron and you craft a neuron for each pixel in your image. So in this case, there are 784 pixels in this image. So we create around 784 neurons. Now those 784 neurons become the first layer in your deep learning model. So we get started. That's great, right? We can give 784 inputs. Now, is that sufficient? No. I mean, typically a deep neural network has, multiple layers, right? So the first layer is essentially your input, but then as you start training and as you start, doing work, you then need to, you identify, the outputs are very different. There is more loss. Then you have optimization, then you apply loss function, you apply hyperparameters, right? So a lot of these goes in creating these subsequent layers. And when you finally reach your the output deep neural network model. Now image is just an example. Text, sound, and everything else can be used as an input, and that's how most of the AI layers are now functioning. Almost everything you see, from speech recognition to visual recognition, is being built using models, and they are being fed into these network layers. Typically there is a technique for subsequent layers, right? As I was telling, why do we need subsequent layers, or what happens in rest of the neural network model, right? So when we are training, for example, once we create a base model, we take the output of the first set of neurons, and then we see that it's not matching the desired output we want, right? So then there is an error, and then we create an optimization function and go with the training again. And you keep on doing this. So that's why we see, training is a very, very compute intensive, and it's a very long process, right? Imagine doing something like this on your laptop. And there are instances, you can run models for training for a week, and it will keep on going without even getting to a place where you are actually able to get realistic results. So that was the context of how typically the training part, or how the model creation works. Now there are typically three paths to creating AI models. One is definitely the pre-trained models. So a lot of the Watson services we have, like speech to text, text to speech, visual recognition, these are all pre-trained models which are deployed as APIs. Then transfer learning, where we actually in case of IBM, for example, this will be where we work with a lot of our customers in different domains, be it the retail, insurance, healthcare. And that's where the technique of transfer learning, where you actually take a pre-trained model, and we have an SME who can actually then retrain that model on a specific domain data, and then you create an industry specific model, right? And last but not the least, the hardest part, which is creating a model from scratch, right? And typically, as I mentioned, you go through this process, you optimize, and you create hyperparameters. If the output matches, that's good. If not, then you go through that process again, and finally when you are ready, you deploy it on cloud. Now once you deploy it, is the job done? Typically in the application development world, I mean, getting an application into production is good, right? And it's predictable, it's behaving as you wanted. But in case of models, it's a very fluid world. So far, the models have lived in a very constrained world. They have been trained on a data set which is very specific, which can be biased, so that when they actually get deployed in real world and they start interacting with real data, the predictions they give can be vastly different. And they start giving biased results, or they are prone to adversarial attacks, and the results are not accurate. So you need to have that whole loop of being able to evaluate them, start another training, retrain them, redeploy them. So I think the whole point is that this is a process which is very compute intensive, very time intensive, and it needs a lot of effort. Now, how can we speed up? So first we take a multi-framework approach to deep learning. So just so as to make sure we are tapping into the large community of developers, AI developers, and data scientists. So TensorFlow, Caffe2, PyTorch. Right now, if you see, the community is mostly rallying around TensorFlow and PyTorch. Then MXNet is very popular as well. And the subsequent launch of PyTorch 1.0, right, which is going to combine the Caffe2 and PyTorch into one code base, is being anticipated. So with that, coming to specifically what Fabric for Deep Learning does. So essentially the idea is, be able to provide a scalable, resilient, and fault tolerant deep learning framework, because we need to work. This is a world where we need to work with multiple deep learning frameworks. TensorFlow is dominant, but PyTorch has a strong community. MXNet has a strong community. When we go to certain geographies, for example, in Japan, Chainer is a library which is very popular. If we go and work with customers in China, Paddle gets used a lot. So this is a world where there are multiple frameworks. To be able to leverage them, and then to be able to leverage the underlying capacity in the cloud so as to speed up that compute intensive training process we talked about, right? So as to be able to distribute the deep learning training process so that we can get the benefits of a distributed infrastructure and the Kubernetes scalability to actually reduce the training time. So in case of Fiddle, it's built using the microservices architecture on top of Kubernetes. So the control plane of Kubernetes, there are microservices which are deployed, and then we have the data plane which are launched when a training request comes in. And the data plane essentially, acts as a batch training model. So when a training request comes in, we intercept it, and then based on the request, whether it needs GPUs or CPUs under the covers, that's when we launch the training process. And once the training process is complete, all the resources are released back. We have been testing it on, definitely community Kubernetes distributions, Kubernetes, DIND, IBM Cloud Public, IBM Cloud Private, both using GPUs as well as CPUs, right? And we leverage heavily the Kubernetes integration with NVIDIA GPU device drivers, right, which is now becoming the de facto mechanism to make Kubernetes work with GPUs out of the covers. And as I mentioned, the main key benefit is in that, we are able to leverage the compute as and when needed. So this is, a serverless model for batch training, where essentially, you're launching your batch training jobs when the requests are coming in, doing the job, and then releasing the resources back to the cluster for other workloads to be able to consume them, right? And we are distributing this model training across containers. So this is high level view of the current architecture. So as you can see from the control services or control plane services, we have REST APIs which are front ending the whole interaction. You can get started either with a CLI through a Jupyter notebook, which is very popular in the community for AI developers and data scientists, or you can come in through a browser, right? And once there, then you are able to interact going through the trainer service lifecycle manager and be able to launch what we call learner pods. Now, within those learner pods, we have the sidecar processes which help to able to collect the logs, the evaluation metrics, be able to monitor your training progress, and be able to send it back. At the very bottom of it, you see what we call parameter server, Horoword, OpenMPI. So when we talk about distributed deep learning training, there are different approaches which are very popular in the community. So for example, TensorFlow uses an approach called parameter server approach. That's the default mechanism in TensorFlow, where when you launch distributed training, multiple learners, they coordinate among themselves. They actually send their weights and the gradients as they are doing the training to a parameter server, and the parameter servers are the one which are coordinating amongst themselves. When you look at an alternative approach like Horoword, which came from Uber, right? So it uses OpenMPI under the covers, and that's essentially a lot of peer-to-peer sync happening where we are doing scatter and gather. So all the learners are coordinating among themselves, finally reaching to a conclusion in terms of syncing the weights and the gradients. So different mechanisms are popular based on what framework you use. PyTorch heavily relies on an approach which is more OpenMPI driven. TensorFlow relies more on the parameter server approach, but then different frameworks have their preference over what they want and what they use heavily for distributed training, and then the performance benefits you can get out of it. Very quickly, yes, this has been part of IBM research. It has been in incubation in IBM research for last 2 years. A lot of research papers out there for those who want to look at performance numbers, the download times. All of these are some of the older numbers, and we are getting much better performance. We are running this and throughout internally IBM every day, like hundreds of researchers launching like multiple hundreds training jobs every single day on this particular cluster. So it's being used and leveraged heavily. It's also the core of a product, deep learning as a service within Watson Studio. Now, Watson Studio is beyond just deep learning. It provides machine learning runtimes plus a lot of data scientist tools like Jupyter, RStudio, SPSS Modeler. But then all of this is learning on top of Kubernetes, leveraging NVIDIA and Docker under the covers. I was probably skip some of this part and come to the parts which are more relevant to the Kubernetes community, right? So, for example, typical example of Watson workloads, running on Kubernetes, we have around 12 Watson services or apps, which are now represented as 800 plus Kubernetes services on IBM Cloud. Now, each service like this, typical model is, if you can see, it's around 3,000 plus pods and around 500 plus nodes. That's the scale at which Watson is leveraging Kubernetes under the covers on IBM Cloud. So our whole Watson infrastructure is right now running on top of Kubernetes, and it's leveraging and using Kubernetes heavily. So it's very, very relevant. Kubernetes is very, very relevant to our whole AI portfolio. I think I talked about the architecture briefly. So essentially, as I mentioned, the REST API is the gateway to this world. Then we have Trainer, which provides the gRPC interface, and the Trainer is also responsible for launching the training jobs, halting them, terminating them. It stores a lot of the data in the MongoDB, right, from which can be used for billing and chargeback purposes. Then we have the Lifecycle Manager, which is essentially the brain, which is doing all the orchestration of taking the request, figuring out what job it is, whether it's a TensorFlow job, PyTorch job, what kind of capacity it needs. It needs CPU, CPU, and then being able to launch them onto the Kubernetes cluster. Each training job is essentially a combination of what kind of learner it is, whether it's a TensorFlow learner or a PyTorch, etc. Then we have controllers and log collectors, and log collectors and job monitors are typically the sidecar processes, which help in terms of collecting all the evaluation metrics and the training data, which is then streamed back to the ELK stack, right, and then represented on the GUI. So a few of the recent release updates, right, we have been working with the community. So for example, we partnered with Uber. Uber has a mechanism for distributed training called Horoward. So we announced that support at OSCON in Portland, where essentially you can leverage Uber's Horoward mechanism to do distributed deep learning training using both TensorFlow and PyTorch. The announcement was around the PyTorch support, which we did. Then we also partnered with H2O.ai. H2O.ai is very popular in the machine learning community. They provide a lot of machine learning algorithms, including GBM, GLM, etc. Right? So all of those are now can be invoked from Fiddle using the same CLI and same UI. And then we have a partner on the model serving side. So typically, Fiddle is focused on the distributed deep learning training. But beyond training, once you have trained your models, you need to deploy them for inferencing, for serving, so that end users can target those APIs and leverage those models in their apps. So we partnered with a community provider called Selden. They are a startup in UK, and we are doing some great work together in this area. So I think we talked about this, and another thing which we recently launched was integration with Adversary Robustness Toolbox, or ART, that actually allows you to launch attack methods on top of your trained models and find vulnerabilities. And then you can implement defense mechanisms, retrain your models. So that integration was announced as well. What are we focusing on in the next few releases? So essentially, so what we found, and that's probably a call we want to make to the Kubernetes community in general, is that the default Kubernetes scheduling mechanism is not suited, or I would say, it falls short for batch workloads or AI workloads or data intensive workloads. What we are finding is that, when we are launching distributed deep learning training, the default scheduler, it doesn't have the notion of, priority in terms of being able to, prioritize certain jobs over others. The notion of gang scheduling, where essentially, some things either go together or they didn't go at all. The notion of preemption, that once you have scheduled a few things, you want to deprioritize something from the queue and then give priority to someone else, or being able to be resource aware. So a lot of those things, which are not there as part of the default Kubernetes scheduler. So community is right now focused around a project called Kuberarbitrator. So that's something, an open source project being heavily driven by IBM, but now it's a Kubernetes incubation project. And, we are glad to, start seeing some contributions now from Google as well around this. So, and I believe, this is becoming now the de facto open source community driven project for the notion around batch scheduling or gang scheduling, as I was talking about. So, right. So a lot of the things around, support for job dynamic prioritization, time-based scheduling, being able to preempt or resume jobs, being able to place jobs in a topology-aware environment, right? So a lot of those notions are being built into this, and it brings also, the capabilities around gang scheduling, etc. So this is now where a lot of the effort is focused on our side, and we are working with the community to make sure, this becomes the scheduler for batch workloads and AI workloads within the Kubernetes community. So, I would request all of us, who are building machine learning platforms on top of Kubernetes to actually, rally around this and contribute to this particular project. Then the other work which we are doing, and again, this is a call to action to the community around Jupyter Enterprise Gateway. Again, this is focused around leveraging Jupyter notebooks in an interactive way with Kubernetes clusters. So essentially, what we are seeing in the community, Jupyter notebooks have become the de facto standard, right, for a lot of data scientists and AI developers. There is definitely RStudio and Anaconda, which have their own fan following. But within Jupyter notebooks, there is a project which we have called Jupyter Enterprise Gateway, which was again initiated by IBM, and now it's a top-level project in the Jupyter ecosystem. And what it allows you is to actually be able to consume resources from a target cluster like Kubernetes to be able to launch, training jobs in an interactive manner. So I would encourage, for folks who are looking at the intersection of Jupyter and Kubernetes in general, how to make them work together, they should look at this particular project, Jupyter Enterprise Gateway. Yeah. So that we will go and do a quick demo, and the demo is centered around, the integration which we are doing in Fiddle around Onyx as well. So for the folks, in this field, Onyx is quickly becoming the de facto standard around model interchange format. So essentially, as I was talking about these multiple frameworks, they have their own model structures. So Onyx is an attempt. It started from AWS, Facebook, and Microsoft, and now there is a big community which has formed around it, and the effort is to standardize model formats. And within that, IBM actually contributed the TensorFlow backend to export the model in an Onyx format, because right now we don't have officially Google on board onto this project. So to support TensorFlow in the Onyx world, IBM is doing a lot of work, and the first attempt was actually, to contribute that backend to be able to export the model in Onyx format. And if you see with the frameworks which have native support for Onyx, it's just a single line to convert into Onyx format. The fact that we don't have it natively in TensorFlow, we need to write a few more lines, because we need to transfer the data from memory to a persistent disk, and then do the conversion we need to do. And once you have the models in Onyx format, it's very simple to load the Onyx model and run it with different backends, right? You can run it with any backend of your choice. And what we are going to show is, how you can run this complete pipeline. So that means, you can run Fabric for deep learning or Fiddle on top of Kubernetes. You have the model serving layer, which is Seldon, which is running on Kubernetes. And by the way, Seldon should be of interest to folks who are looking, on the model serving on the open source side. A lot of notions around, being able to serve models on top of Kubernetes with the notions of A/B testing, canary testing of models, the notion around, multi-arm bandits, canary releases, they're all built in, and they're doing a lot of work around that side. And we are leveraging, our community partnership, to drive some of that together. So with that, Tommy, do you want to go into the demo very quickly?
Yes, no problem.
I will
Hi,
stop.
I'm Tom. All right.
Should I stop share, or?
You should stop sharing.
Okay.
Hi, I'm Tommy. I'm going to explain a little bit on the demo flows and what we need to do to submit a training job on Fiddles. So for this training jobs, we're going to train on PyTorch examples. It would showcase a distributed training using data parallelisms. And once we train the models, it will store on the flex volume we mounted on, which is on an object storage. And seldom we leverage that flex volume and use that models to serve it on these platforms. So to train a job on Fiddle, we need three components. One is the model files, which specify what kind of algorithm you want to use. And then a manifest files to specify what are the resources and the data location. I will explain that later on. And object storage to store any of your data sets and your model results. So one thing that we asked users to specify on Fiddle is the manifest.yaml, which specify four major components. One is the resource definition, like how many GPUs, CPUs, and learner you want to specify. And then the object storage definition, where you want to store the data and where's your data set located. And then the third thing is the framework definitions to specify what kind of framework you want to use and what's your entry point commands. And last is the evaluation metrics, where you specify what kind of evaluation metrics collector you want to use. In this case, you could use like TensorBoard, or for PyTorch, you could use something else that's specific for that framework. So as you can see, here is our IBM developer Copilot page. You can find more details on the Fiddle architecture over here. And here is our GitHub page, where you can find the details how you could deploy the Fiddle on your Kubernetes cluster. And for this demo, I already deployed our Kubernetes cluster. So let's go ahead to our UI and see how to submit the jobs. So once you land on UI, you just log in with the credentials which that was in your cluster. Yeah, the network is a little bit slow. So once you have it, you see the history of job you have trained, and then you could submit some of the model definition files in a zip, and submit the manifest that specify how you want to train your jobs. And then click submit training jobs. Then you're able to see a new job is submitted on a Kubernetes cluster. You go back over here and look at your cluster. You should be able to see a new learner is created, and some of the helper part will tell you collect all the data and send it to the object storage at the end of the training. And within the training jobs, you can see what you have submitted, what kind of entry command you have specified. I think this job is still pending, but in a complete job, you could also see other logs you have created and like what's the status at the end. And once you train these models, you can deploy it on Seldoms. And then you could create an app. For example, we create an app using just using the REST API from Seldoms. And all the predictions predict using the model we just trained. So for examples, let's see. Let's get a picture. For example, you take a picture like a trouser and you submit it, and then you predict it as a trouser, and all the prediction is happening on the serving part that is served on your Kubernetes instead embedded in your actual web app. And that's the end of the demos. I will give it back to Animesh. Animesh, I think you're on mute.
Okay, so thanks. We'll just wrap up in terms of where we are focused on next. So our focus next is now to look beyond the training aspects and create this what we are calling the pipeline for machine learning or the AI ops. And essentially the as we are noticing, right? I mean, the fact that your models are never ready. You need to retrain them based on either the data is changed or you ran an adversarial test and you found a vulnerability, or after training when you deployed in real world, the model's predictions are not accurate, or the entropy loss is happening, or it's giving biased results. So these models are always in a very, very fluid state where they are almost always going through this continuous loop of retraining, revalidation checks, bias checks, redeployment, monitoring. So for that, there is something which we need to think from a whole pipeline perspective, more so than any other application workload, right? So that's why we are trying to build right now an ML pipeline, which we will hopefully be, getting it out in the open source community soon as well. And it's going to take the notions of the training, the serving with our open source technologies as well as with our community partners, then doing adversarial checks, doing debias checks, and then trying to leverage different popular tools in the community around pipelines, right? So that's the attempt with this. So pretty soon you'll be hearing more from us on this particular topic. With that, thanks again. Thanks for joining. And this is our grander vision of where we are taking Fiddle V next. As I mentioned, there is a start, but this field is much bigger. If you see more so from a Kubernetes perspective, there is a lot of work happening around Kube Arbitrator. That is a project of interest to us. The Intel is doing some great work around Kubernetes Volume Controller, which essentially brings and pulls a lot of data back and closer to the compute resources, so to speed up training. That's a project which is definitely of interest. We also open sourced as part of this effort of launching Kubernetes object storage plugin. So that essentially is what we are using in Fiddle for mounting S3 Flex storage drivers. So that's also available in github.com/IBM. And that's a project where we are contributing for folks who are looking at, how to make the best use of Kubernetes and object storage together. And then definitely, a lot of the innovation coming out of NVIDIA around the GPU device drivers. So a lot on the core Kubernetes side. Then the AI ops layer, which we will be building, right, and which we are testing right now on top. We are investigating a lot and working with Airflow, with Jenkins, but more so around, event-based pipeline structure, leveraging OpenWhisk to begin with, right? But moving forward and looking at other functions and the functions running on Kubernetes, right? Functions as a service platforms running on Kubernetes. So a lot of innovation happening at that particular layer for folks in the Kubernetes community, and definitely at the very top layer, all these notions around, the distributed deep learning training, monitoring, metrics logging, serving in model serving in cloud, offering being able to launch AI developer tooling on top of cloud. That's, the area where we are focused on moving forward. So thanks again. And thanks, Ade, for having us here.
Yep, no problem. Thank you so much, Animesh and Tommy. And I guess you can take some questions, Animesh?
Yeah, definitely.
Yeah. So I do have a couple of questions. If anyone else has any questions, please go ahead. By the way, this was great. So thank you so much. Lots of good learning here.
Thanks.
Yep. Questions. Well, I guess I had a few questions. Just wondering from again Kubernetes perspective. So I know you mentioned that the training and then once the models are trained, right? They in our case in the demo, it's handed over to the Seldon. So is that two different Kubernetes cluster running? I was just wondering from more like on Kubernetes particular version perspective, right? So say you're training on a particular version of Kubernetes, that's where your jobs are running, right? And again, I think the way I understood the training takes long, right? I mean, I guess I mean, hours, days, assuming. But then when you run that, does that has to be the same version sort of thing, same cluster or no?
No, I mean, for our demo purposes, for our testing purposes, we use a single cluster. And Tommy, correct me if I'm wrong.
Yeah,
But
we use a single cluster. It doesn't matter where you deploy the seldom and the fiddle, because essentially the model is stored in object storage, and as long as they use the same, they will use the flex volume to mount the same volume. So it doesn't matter where you deploy
and for production, you would want your whatever the machine learning serving and inferencing platform is. In this case, it is Selden. We have our own machine learning platform in Watson called Watson Machine Learning Serving Platform, which is a hosted offering. We don't have it in the open source, but for production, the recommendation would be you run your serving on a different Kubernetes cluster, ideally because that's where the application developers are consuming your deployed production models. Training is the pre-process part, and you would want it to be on a different cluster with different set of resources. But again, for our dev test and demo purposes, we use the same cluster.
No, thanks. And does the version of Kubernetes matter, or no? So you train it on a particular version of Kubernetes versus when you run it, if it's the same, like say 11.1 or versus 12.1. If people moved on, or backward compatibility kind of things. So that's more like an user side. They need to take care of it.
I mean, not in the context of the bridging the training and the serving world, right? So once you have trained your models, it doesn't have any notion of the Kubernetes, right? The end output is a trained model, which you then take to a model serving or inferencing platform and you deploy. Now for Fiddle itself or Selden itself, the versions of Kubernetes they will support, that definitely varies, right? Do we have the latest version of Kubernetes working with Fiddle? Probably not, probably yes. So right, and the same with Selden, right? Unless we test it. So that keeps on changing. But for the model itself, they are totally unaware of that Kubernetes was part of the training process or Kubernetes is part of the serving process. They are agnostic to the Kubernetes versions or the kubectl command lines, as you mentioned.
Gotcha. Thanks. Actually, that's what my second question. I was just wondering, and I think Fiddle provides lots of abstraction here, right, on top of Kubernetes. So, for the ML machine learning developers or data scientists, do they really need to? I mean, how good they need to be with Kubernetes, right? I guess they really don't need to worry too much about the infrastructure. It's the question. So it's already taken care, right? So for the data scientists, for the machine learning app developers.
No, definitely. I mean, that's definitely the intent here. That
right.
The main intent is that yes, you as a data scientist or an AI developer can probably on your laptop, for example, if you're a TensorFlow developer, you can launch TensorFlow on your laptop, right? But you're constrained by the capacity in your laptop and your machine on whether it has a GPU or not, and you can probably have something which runs for 5 days. Now, so why would you then look for a cloud? You probably want to speed up this, right? And you want to, take the capacity of multiple GPUs. And you don't want to be dealing then with the cloud primitives. Like, you don't want to be using kubectl command line to interact with Kubernetes, crafting, Kubernetes YAML files. So that's the attempt to abstract a lot of that, right? So essentially you have an entry point using a Fiddle CLI or the Fiddle UI, which Tommy demoed, right? Which is essentially when you go to that UI, you are essentially, pointing to your data on which you need to train and, your model, and then saying, launch distributed training. So user is not interacting with Kubernetes at all under the covers, right? Once it is deployed. For the deployers who are deploying Fiddle, yes, they need to understand Kubernetes, or they at least should have a Kubernetes running, right, before they can deploy Fiddle. But once deployed for AI developers and data scientists, they are interacting with Fiddle and they don't need to know about Kubernetes.
Gotcha. Yeah, thanks, Anish.
This is Khaled. I just have a question. Like when you deploy it in Kubernetes, you have these training jobs and so on. Are they leveraging the host network, or are you going through the overlay network for communication between all the components? I know there, like with MPI and so on, there's overheads associated with that. I'm just wondering if you encountered issues around scale or performance in your larger environments in Kubernetes itself?
So I think, so typically, the way the teams are structured, when you go and coming to the power team where they are actually, trying to run this. So when you leverage things like OpenMPI for distribution, right? So MPI is a protocol which operates at the very low level of machines, right? Where essentially when you're doing distributed training and syncing weights and gradients, so MPI is aware of the topology, the hardware topology, right? The network topology and the bandwidth, and it takes that into account as it is trying to distribute the training, right? So definitely at those low level layers, right, based on the protocol you choose for your training, right, that will have an impact. But when this is a service which is hosted in cloud, right, but you're not deploying something, on that case, right, we do the default tuning and the default parameter settings, right? In that case, you are not directly being impacted, but it's mostly the overlay network, right, on top which we are taking. But yeah, for customers, they choose, for folks who are using, either deploying it on their own, or for example, when you are doing something homogeneous hardware like Power AI, then you choose your settings. But for the most part, then OpenMPI is what is being chosen, because that gives you the benefits of knowing the hardware topology and the network topology, and it works accordingly. Yeah.
Okay.
Well, I have one last question. Sorry, many questions, but hopefully a quick one. So with the job, right, the training Kubernetes job, is that we just use the Kubernetes manifest files as such, or is there any FIDL domain specific, language DSL? And I was running more with the Kubeflow perspective. So Kubeflow, they use a lot of those CRDs, right, the custom resource deployers kind of things. FIDL, these jobs are more like just Kubernetes manifest or something else?
Yeah, so Kubeflow uses CRDs right now to implement, when they launch a distributed training. In our case, right, yes. So essentially, when you define a job and FIDL, you use manifest run YAML file which tells FIDL where is your object storage, right? Where is the data file in that object storage? Where is the model stored in that object storage, right? What framework you are using, and whether you want to use GPUs or CPUs. Is there a cap limit you want to put, right? So that's the DSL which FIDL accepts, right? Now beyond that, once it goes, it is not implemented using CRDs, right? So it is launching these learner pods as microservices during runtime, right? And for that, we are leveraging, by default, the Kubernetes scheduler. Now, what we are trying to do in the next iteration is rallying around Kube Arbitrator. Now, Kube Arbitrator is being implemented using CRD. It's what is, being leveraged now moving forward as the scheduler for FIDL, right? So that will allow you to launch, batch jobs. And then top of Kube Arbitrator, we are building the concept of what we call queue jobs, and then having our own algorithms on top of that, right? So that's implemented using CRD. But right now, yes, anything learner pod which you are launching right now, it's coming up as microservices or Kubernetes YAML, which are launching pods on top of Kubernetes. Yeah.
Gotcha. Okay, that was very helpful to know. Thanks. Any other question, guys? I know we're reaching to the time limit. A few more minutes.
I have one more question.
Sure.
On the Kube Arbitrator project, and it looks like it leverages priority classes, which are new in core Kubernetes 1.11. Now, I'm just curious what the plan for Kube Arbitrator, both from your perspective and then the community's perspective. Are they looking at getting this type of scheduler being able to go into core Kubernetes, or is this always going to stay a contributor project? It seems like it's relatively easy to install with a Helm install. You can put it on your cluster, but I'm just trying to gauge the interest in getting this easy to put on, our cluster, any Kubernetes cluster out there.
No, and that's a good question. So it's right now Kubernetes incubator project. If you see, there is, in fact, it's sponsored by Joe Veda and others from Heptio, right? Plus, if you see the contributors list, you'll see, folks from Kubeflow as well, if I'm not mistaken, are now leveraging. So I think, there is a parallel stream where, Kubeflow is also leveraging, because they also encountered that, for batch workloads or ML workloads, the default Kubernetes scheduler is not sufficient. So from that perspective, if you see, we are heavily behind it. We are leveraging it. In fact, right now as we speak, there are for the whole internal deployment of deep learning as a service, on Watson, right? We are testing Cube Arbitrator for a production batch scheduler, right? So it's yet not rolled out, but that's the intent. Now, if the major community providers who are providing this, they are rallying around it, then it's probably a matter of time before it moves into the main Kubernetes stream, and that's what we will push for next, hopefully as we move forward. But it's very clear right now. I think that looks like the only valuable solid alternative for the deficiencies in the default Kubernetes schedule. And it has been presented. I mean, there is an ML working group of Kubernetes, right? So we presented it there as well, and hopefully, there were a lot of folks from other companies, Intel, Cisco, etc. We didn't hear anybody having a strong alternative at this point to that, right? If there is some other community project, if anybody is aware of, we would be glad to look at. But right now, it looks like Cube Arbitrator is for batch scheduling. Yeah.
All right, thanks. All right, so if there's no other questions, I just had one more update for the SIG. Last couple of meetings we were talking about the SIG charter, and the folks new on this call, all Kubernetes SIGs are required to have their own charter, and we also had a PR in progress defining the charter for IBM Cloud SIG. It was reviewed by steering committee, so all the SIGs were provided to steering committee members, and we did too. So it got merged just last week. So I just wanted to update everyone. And that seems like the only other item in agenda, open discussion there. But I mean, we definitely used the time very well today. So there's no other question. I guess we can get the 5 minutes back.
Yeah, thanks. And I just realized no matter how fast I go, this presentation is going to take that 45 minutes to an hour. So yeah.
No, this is good.
20 minutes time frame.
No, this is great. Nimesh, Khalid, Phil, anyone, any comments?
No, it's a great presentation. I really enjoyed it. I think it was good content, and especially for the Kubernetes part, understanding what you guys are doing, leveraging that.
Thanks, Khalid. And thanks, Sadeh, for having us here.
Well, absolutely.
Thanks very much.
Yeah, thanks for presenting. Well, everyone, thank you so much. I'm going to stop recording. Have a great rest of the day. Thanks for joining, and talk to you later.
All right, bye.
All right, bye.
Thanks. Bye.